All right, time now to grapple with the traction integral. So let's recall what it looks like. It is the following. It is sum over the spatial dimensions so sum now over E belonging to each of these ones, right, of okay, now, and we do an integral here, partial omega E T bar I W H I T bar I ds. Okay, so what that tells us is that it's really this integral that we need to consider. Okay, so we have this one. Remembering that we do not have here a sum implied. Okay, that's straightforward. We need to do that as integral over partial omega E T bar I. For WHI we have sum over A NA C A I E, that's WHI T bar I ds, which is sum over A C A I E integral partial omega E T bar I NA T bar I ds. All right, and now we recall the cases that we've actually considered before, right? So we just need to recall them. I don't think we need to re-motivate and sort of discuss them in great detail again. So the situation that we tend to have in general is this. That is omega E, and let us consider the general situation where straight away let's consider the general situation where this face is the one of interest, right? Partial omega E T bar I. Okay, so what this says is that traction component I is being controlled on that surface. Right, and I've drawn it, hopefully it appears to you that it is at an angle, if that is our basis set. Okay, right, so that is the general situation we have. Recall, of course, and something we know and we've looked at before, which is that we are somewhat saved by the fact that as I've drawn it, perhaps that one can think of that face as coming from this one, right? So for the way I'm drawing things here, I am implying that the face of interest is a is this phase, right? It is a C2, C3 phase, right? So this is partial omega C T bar I, sorry, T bar subscript I for this particular element, all right? And so it is that we know where to compute this this integral, except that we also know that when it comes to constructing our mapping, we may need to construct local coordinates just in order to get the Jacobian of the mapping correct, right? So let's suppose that in this setting I'm calling that x tilde 1 and the x tilde 2 direction, right? Actually those vectors really are, each should probably be written as e tilde 1 and e tilde 2. But anyway, those are the directions that we have, okay? And from this phase to that phase, we may think of there being a map that I denote as J sub S, okay? See. All right? Okay. So we have all that, and of course I okay, I'm going to use that in a second. Before I do that, I just want to point out that I also need to recall that the sum over nodes may not need to be over every single node, right? It may need to be only over that set of nodes, right? And previously we've used the notation that this node A belongs to the set A sub n, right? To say that that is one of the nodes corresponding to a surface with a Neumann boundary condition on it, right? So really the sum is over A sub n, as is this one. Okay, all right. So using this map, the way we would construct this integral would be this. Now, the integral here would be over partial omega C T bar I, and for the way I've drawn it here, I'm suggesting that that is C2, C3. Okay, right? That is the C2, C3 plane, right? So then we have here our NA T bar I, right? And now we're going to do the integral over ds sub c, right, which is the elemental area on the partial omega c t bar I face in the bi-unit domain. And I've left some blank space here because I know that I need to put in here determinant of Js. Okay, because Js maps a surface to a surface. What is the order of Js? What kind of a tensor, or what kind, if you think of it as a matrix, what kind of a matrix is it? Js is a 2 by 2 matrix. Okay. So Js, using the notation that we've used, is GL2. Right? It maps two vectors to two vectors. Okay, it's probably useful for me to point out in addition that for the way I've constructed this particular example, DSC, it's something I stated already, but what is DSC? It is DC2, DC3. Okay? and therefore that integral would be over C2 and C3 going from -1 to 1. All right. Okay, so we have all of this, and what we need to do is essentially go ahead and construct our vector representation of this. Okay, so in constructing the vector representation, I am going to write this as now. I'm going to write this as follows. I'm going to write it as a sum A belonging to A sub n. Okay. Okay. Let me write this as C A I E. Now that entire integral, once I evaluate it, I am going to write as f. I'm going to write a t bar here, which just is reminding us that this particular type forcing vector comes to us, this particular forcing comes to us from the traction. Okay, it is an I component. Okay, and it also involved node A. Okay, so that entire F with all kinds of decorations on it now, with subscripts and superscripts galore, actually it has just 3 of them, is the result of that integral that we carried on, right? That the integral over the surface. Okay, all right, so this is what we have. Now, where does this go? Remember where this all came from. And in order to remind you of it, let me just go back to the previous slide. This is where it came from. We have at the very top of our slide here the original integral from which this came, right? And note in doing this that really there is a sum over the spatial dimensions as the outermost sum here. Okay, and then there is the inner sum over the element integrals. Okay, so what this is suggesting is that when it comes to assembly, okay, we will first assemble the contributions from each element and then account for the sum over the spatial dimensions. Okay, but before we finally do that, there is one thing we can do which is going to get us rid of the restriction to the special set A sub n. Okay, right, and what that involves is the fact that okay, so let me now say the following. Actually, let me do one thing. Let me put a bar on this f first. Okay, because what I'm going to do now is just rewrite that as a sum over A. Okay, now I'm going to say that this sum runs over all the nodes in the element, C A I E F T bar A I. Okay, and what I mean here is that F T bar A I equals the F bar that I calculated on the line above if A belongs to AN, right? Right, and it's equal to 0 otherwise. Right, and you will probably recall that this was the approach we used when we constructed the contribution from the Neumann boundary condition also for the scalar problem. Okay. All right. So what have we here? We are now in a position to look at our total finite dimensional weak form with all these element integrals accounted for. Okay, so right, it is the following. We have sum over E, C, E, so let me see, sum over E, oh right, we have one more thing here. We have sum over E, we also have a sum over A comma B, C, A, E transpose, right, K, A, B, D, B, E. Okay, this is the contribution from the left-hand integral, equals sum over E, sum over A, C, A, E transpose, F internal A, okay, and plus sum over spatial dimensions, then the sum over elements belonging to the Neumann boundary condition corresponding to that particular spatial dimension, right, and right, and then we have yet another sum here over A, right, and this is over all the nodes, C, A, I, E, F, T bar, A, I. All right. Okay. Now, in writing all of these, I did notice a few minutes ago that when I introduced this matrix K, it really corresponds to a particular element because it arose from a specific element integral, right? And it arose from the element integral for element E. So strictly speaking, I need to have it an E there, just to remind us that it is the contribution from that particular element. Okay, likewise here, and likewise if there's any room here for more indices, for more subscripts, there we go. Okay, so this is where things stand. The next step that I'm going to take is one in which I am going to collapse, well, not collapse, actually expand out these vectors. Okay, and in order to do that, let's just let's go to a new slide.